Bioelectric potentials. We've already seen the definition of bioelectric potential. What is equilibrium potential, Nernst equation, resting membrane potential, and local potential. This video will show about what is action potential. Before we go into this topic per se, let's see a couple of points. Every living cell is said to be polarized, with the inside of the cell relatively negative when compared to the outside, which is called as the resting membrane potential, which is a negative value. But when a cell is stimulated and it is an excitable cell, this electronegativity decreases, that is, the inside of the cell starts to become positive when compared to the outside of the cell. However, it starts to return back to its resting state, which we call as repolarization. When there is a decrease in the electronegativity, we call it as depolarization. Returning back to the resting state, we call it as repolarization. However, if it overshoots beyond the negative value of the resting state, we call it as hyperpolarization. Whenever we stimulate an excitable tissue, if the depolarization that occurs is less than the firing level, we call as a local potential, and when it goes beyond the firing level, we call it as an action potential. So what is action potential? It's the transient change in the resting membrane potential, which we see when we stimulate with an appropriate stimulus on a nerve or a muscle cell. So we call both of them as an excitable cell. When we record an action potential with time on the x-axis and the voltage change in the y-axis, this is how we get a graph. Before we go to the graph, let's take this excitable tissue has a resting membrane potential of minus 70 millivolts, and it has a firing level of minus 55 millivolts. We give a threshold stimulus, we start to have a recording like this, which we call as a recording of action potential. This graph has its peak maximum at around plus 35 millivolt. That means it has spanned from a negative value of minus 70 towards positive value of plus 35 millivolts. From the point of stimulus to the point of initiation of any change in the membrane potential, we call it as the latent period. The initial slow rise in this membrane potential from the RMP to the firing level, almost a change of around 15 to 20 millivolts, we call as the slow depolarization. When it reaches this firing level, something happens that this membrane potential starts to rise rapidly from minus 55 to plus 35, so we call it as a rapid depolarization. Once it reaches a positive value of plus 35, it again starts to become negative, first rapidly called as rapid repolarization, then slowly called as slow repolarization. However, this doesn't stop once it reaches the same RMP of minus 70, but it overshoots it, so we call it as hyperpolarization, but it returns back to its resting state. Now, what's the ionic basis for each of these states? It was slow initially after the latent period because of the slow influx of the sodium ion. So a positive charge from outside is starting to enter into the cell, making the resting membrane potential from minus 70 to reach the firing level of minus 55 here. Once it reaches the firing level, it opens another channel which is called as the voltage gated sodium channel. These channels make the rapid entry of sodium into the cell. That's the reason why the potential, which was slow, now rapidly raises from minus 55 to plus 35. Once it reaches plus 35, this voltage gated sodium channel closes. However, the voltage gated potassium channel opens up, making potassium leave the cell. Then we have similarly a slow potassium efflux, which results in the slow repolarization and hyperpolarization. If we have a recap of what we studied during the resting state, inside of the cell normally has more potassium than outside, and outside has more sodium than inside. However, now if we see there is more sodium inside and less of potassium inside. So how do we change it back? To the resting state. We have the sodium potassium pump, which pumps 3 sodium out of the cell in exchange of 2 potassium back into the cell, making the cell come back to the resting membrane potential. I hope this video was easy, useful, and you can remember the various phases and how each of these phases is linked with opening or closing of a channel. Thank you. So what we have seen now are we know how to define an action potential, what are the phases of action potential, and what is the ionic basis for each of these phases. For additional easy understanding, these are animation videos of action potential. Hope you enjoyed the video. Thank you.